In this video, we are going to go over an idea in counting theory called combinations. Combinations put together kind of build off of the fundamental counting principle and something we saw with arrangements, with what to do with repeats, and also permutations. So to see how all that connects, we're going to kind of start and review all those things. So first of all, understanding that arrangements are just arranging things in a particular order. So we saw this when we arranged 10 cars in a 10-car garage. We had to decide which car went in the first slot. There would have been 10 choices for that. Which car would go in the second slot? There would be 9 choices for that because we've already parked one car. And all this notion is built on the fundamental counting principle of just deciding how many options you have for the first slot, how many options you have for the second slot, how many options you have for the third slot. That's just going down because you're using up your options as you go. Then a particular thing we did with arrangements is what happens when some of the people, objects, or characters that we're arranging are indistinguishable. So for example, if you have a password, it's probably not a password because passwords usually you can't just rearrange them, but it's just an interesting idea. So let's say you have a sequence of numbers. Okay, I just wrote one out here real quick. 2, 5, 7, 2, 3, 4, 2. Well, then if we ask the question, how many different ways can we arrange this? What we have going on here is we have 3 2s. So when we rearrange things, if a 2 ends up in the same slot as a different 2, the arrangement is essentially the same, though if we just count it strictly with the fundamental counting principle of, counting down, or in this case it would be a 7 factorial, we're over counting because like if I call this my first 2, this my second 2, and this is my third 2, if I switch 2, 1 and 2, 3, I have the same arrangement, but I would count that twice if I'm just doing 7 factorial. And so what we saw is we have to divide out the repeats. And so then how we know how many to divide by is here I have 3 repeats, so there are 3 factorial ways to arrange that. And so we would take 7 factorial, the number of arrangements there are, and divide that by 3 factorial to get rid of those repeats. So here we're dividing by 3 factorial to get rid of the repeats of the different ways of arranging all the 2's that are essentially the same. After that, we turn to permutations. And permutations are basically arrangements where we don't use up all the objects. And actually, some authors, textbook authors, you talk about permutations and arrangements as the same thing. They just call them all permutations, but I like to distinguish the two for reasons. So permutations, it's the same as arrangements where we're arranging people, object, characters in a particular order, but the distinction I'm making here is where we don't use up all of the options we have to choose from. So we're still arranging things in a particular order, and I do want to talk more about that word order because it's not always about order. Sometimes it's about the job we're selecting them for. So for example, if I have 10 folks and I'm selecting them for the president slot, the VP slot, and the secretary slot, so I'm choosing from 10 people, then I have 10 choices for the first slot. We have 9 choices for the second slot, and we have 8 choices for the third slot. So, this is where if you overthink it, you could argue, well, I could choose the vice president first, and then I would have 10 choices for the vice president. So it's not about order, it's about that the slots are named. So even if I choose my vice president first, then I would have 9 choices for the president and 8 choices for the secretary. I'm still multiplying all that up. So it's not that I'm choosing them in a particular order. It's that I'm choosing them for a particular job, or they're going into a particular named slot. So sometimes instead of order, I like to talk about the slots are named. So here, President, Vice President, Secretary. Now the slots could be named as my favorite friend, my second favorite friend, and my third favorite friend. So that feels more like order. Or with a password, the first character of my password, the second character of my password. So sometimes it very much is order, but sometimes it's not so much about order as it is that we've named the slots. Okay, so here we can just use our fundamental counting principle where we stop counting all the way down because we don't use up all the options. And I really think that's the simplest way to conceptually think of permutations. But another way that permutations are thought of is that we do a full arrangement. So in this case, if I'm selecting 10 people for the job of President, Vice President, and Secretary, a full arrangement, I would arrange all 10 of them. Okay? And then I divide off the ones that aren't going to get selected. Now, if I write this out long ways, I get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm really proud of myself because I wasn't sure if I could count backwards like that without messing up. Okay, so the point of all that is we can see that the 7 and lower cancels off, and then that just leaves us with the 10 times 9 times 8. And we already knew that. We had that right here. Okay? So I actually am not a fan of doing it this long drawn out way. I'm just showing it because it builds the concept that we're working towards with combinations. Alright, so the idea here is we are dividing out, right here, we divide out the unused people, objects, or characters. Alright, so here we're dividing by 7 factorial because we only need 3 things to choose from. Alright, now all of this, why I'm talking about all this, is up here with the repeats. In arrangements, we talked about repeating where we divide out the repeats. And then with permutation, we divide out the unused numbers. Combinations are going to put both of these ideas together. So with combinations, we'll end up dividing out the repeats, and we'll also divide out the unused numbers. Alright, so all of that was review to lead up to how combinations we end up dividing by 2 factorials. So let's go ahead and clear out the screen and get started on combinations. Alright, combinations are where we're selecting our people, objects, or characters, where the order they are arranged does not matter, or the role that they are selected for is all the same. I tend to like to think about it as the role and not the order, because when I was first learning this, the idea of order kind of confused me, because I would argue that order doesn't matter with permutations, and I could argue that it does matter with combinations. I just overthought it. So I like the idea of the role, or this notion that I've talked about where the slots are named, or in this case the slots are not named, or they're all the same name. So for example, let's say I have 10 friends and I want to choose 3 of them to go to the movies with me. All 3 that I'm choosing are getting to go to the movies. They're all getting the same result. Or if you have 10 colleagues at work and you're selecting 5 of them to be on a committee, they all get the same job in the end. It's not a vice president, president, secretary sort of thing where we're handing out different jobs. They're all going to be on the committee. So they all get selected for the same role. So it doesn't matter what order you select them in. Alright, so I want to do the 10 friends and I'm selecting 3 of them to go to the movies with me example. So my 3 friends that I'm selecting to go to the movies with me are Bob, Tom, and Hank. Okay, so I'm selecting 3 friends to go to the movie with me out of 10. Now, if it were a permutation, what I would do to figure that out, I would just do 10 for my first choice times 9 for my second choice times 8 for my third choice. Or the way I just showed you, you could do 10 factorial divided by the ones you don't use. Okay, so this is if it's a permutation. It's not a permutation. So we're going to have to do more to it than this. But if it were a permutation, this is what we would do. And remember here, what we're dividing out here is the unused. But here, with permutations, that assumes we're selecting these people for different roles or different tasks, or we're saying that Bob's my favorite, Tom's my second favorite, and Hank is my third favorite. But that's not what we're saying here. We're saying they're all going to the mall. Did I say the mall or the movies? I don't know where they're going, but they're all going the same place. So what I'm getting at is if I select Bob, Tom, and Hank, that's the same thing as selecting Bob first and then Hank and then Tom, because again they're all going to the same place, so it doesn't matter what order I select them in. So there's several different possible arrangements where I have selected them in different orders. So for example, I could select Tom first. So if I select Tom first, then I could select Bob or Hank, or I could select Hank or Bob. Or I could select Hank first. And if I did that, I could do Tom second or Bob second. So there's all these different orders that I could select my 3 friends to go to the mall and watch a movie in the theater at the mall. You like how I did that? Anyways, the order that I'm selecting them doesn't matter though. So all of these selections here that I've listed are the same. They make no difference. It doesn't matter if I say Bob's name first or Tom's name first or Hank's name first. And there are 6 of these. But the way we would figure it out, if I have 3 things and I want to know how many different ways I can arrange these 3 things, that's 3 factorial. Right? To arrange 3 things, I have 3 choices for the first slot, 2 choices for the second slot, and 1 choice for the third slot, equal to 3 factorial, which as we can see here all written out equals to 6. So there's 3 factorial different ways I could select these people, but they're all the same. Okay, so just like we did when we were dividing out the repeats, when we were arranging things that had characters that were the same, here we need to divide out the repeats. So with combinations, I'm going to take what I have up here as a permutation, and I'm going to divide out the repeats as well. So for the combination, I have my 10 friends I'm selecting from. I'm selecting 3 of them. So I need to divide out the 7 factorial. That's the unused ones. But then I also need to divide out the 3 factorial for all of the repeated arrangements that are essentially the same thing. So here, this 7 factorial is dividing out the unused. The 3 factorial is dividing out the repeats. Now, if you're good at looking for patterns, you might notice that the 7 and 3 combine to make the 10, and that's always going to be the case because the 7 is the unused. What we're left with are the 3 we are going to select, but when we count them as an arrangement, we're going to overcount them by how many there are factorial. So these bottom numbers, minus their factorials of course, will always add to give you the top numbers, so they're kind of complements of each other in that way. But why we're dividing by them is different. There's different reasons why we're dividing by them. So it's really important to me that you understand why all these numbers are behaving the way they are. It's not just randomness flying around the screen. So with permutations, I really think it's easier to think of it just with your fundamental counting principle. You have 10 choices for the first one, 9 choices for the second one, and 8 choices for the third one. With combinations, a lot of people like to think of it with all of this. There's kind of a middle ground compromise, and I'll show that in the next example. Okay, let's say there are 15 full-time math faculty. How many different committees of 5 faculty could we form? So I'm just going to kind of think through this a different way. So we're forming a committee of 5 people, so that means we have 5 slots. So if you have 15 to choose from, you have 15 for your first slot, 14 for your second slot, 13, 12, and then 11. And we'd multiply those up. So that's, you know, kind of how we approach permutations. But we're selecting all of these people for a committee. That means that we need to divide out the repeats. In this case, we're selecting 5 things, and the order we arrange those 5 things in doesn't matter. So we need to divide by 5 factorial. So, like I said, this is kind of a compromise approach where we're not having to divide out the unwanted ones. We never include them because when you're thinking through the problem, it doesn't make sense to include them. You kind of intellectually exclude them before you start working out the math. And so then all you have to do is divide by the 5 factorial. Either approach is fine. This one, to me, is just a little bit more simplistic because it doesn't include a bunch of stuff that you then just end up canceling out right away. So the idea here is we do our numerator like we did when we did our permutations, and then we just divide out the repeats of all the different ways of arranging those things, because we don't care about what order they're arranged in. They're all being selected for the committee. So then, to make people happy, I'll go ahead and do out the math on this, but that's really not, in essence, what we're learning here. We're learning how to set the problem up more than how to compute it out. So if we expand the factorial, I like to do these by hand because I think it's simpler than plugging it in the calculator. But 3 and 5 will kill off the 15, and then, you know, we could reduce the 4 here with the 12. That would reduce it to a 3. We could reduce the 2 with the 14, which would reduce that to a 7. And then once you get all that reduced, the denominator reduced out as much as you can, then you can go ahead and multiply that up. It is important to note that with these, the denominator will always fully reduce out because you can't have a fraction number of committees. So you should not end up with a fraction result. So in the end, you end up with 3,003 committees. Now in reality, there's just going to be one committee, but when you're talking about probability, we need to be able to figure out that denominator, which is all possibility. So that's the idea behind these counting problems, is we're trying to figure out all the possible ones so that we can use that for determining our probabilities when we're trying to come up with the number of ways we get what we want on top and all possibilities on bottom. Alright, go ahead and give some of these a try and see how you fare.